palm.
Once again, it's an honor and privilege to stand up here and introduce this year's Lehigh Hinsey Award winner for outstanding contributions to geology, Doug Sprinkel, my friend and colleague for over 30 years. I first met Doug back in 1984. Believe it or not, some of you, where's Rebecca, were probably not even born then, but anyway. But we've known each other for a long time. At that time in '84, AAPG was coming to Salt Lake City for the Rocky Mountain section meeting, and Doug was working for Placid Oil, and I got him to do a field trip stop for us. I was one of the field trip leaders, and we were in the thrust belt area, and Doug had drilled a well in Daniels Canyon near Heber, and so I asked him to come out and explain what they were up to, and it was absolutely pouring down rain, and Doug stood out there by the Whiskey Springs stop, I think it was, picnic stop there along Highway 40, and in spite of the rain, he had logs and seismic and went through the whole thing of his well while we all stood there and freaked, and we've been friends and colleagues ever since, and getting even with each other. We've even attempted to kill each other a couple of times, which we'll cover a little bit later. Doug was, many of you may not know, Doug was born in San Antonio, Texas, and even though he actually only lived there for a couple of days, he's a Texan by right. But he grew up mainly in Southern California. However, he came to Utah in the 1970s and got his bachelor's and master's degrees from Utah State in 1975 and in 1977. He actually did his thesis in the Wellsville Mountains under the late, great Clyde Hardy, and he did it in 1 year. So he's a fast mapper, as they say. As I said, Doug is, I'd like to go through I'm the one who nominated Doug, and that's the reason I'm up here to explain my rationale for, but I'm sure after you hear some of these things that you'll agree with me that Doug is very, very much deserving of this very prestigious and special award. I kind of divide up into 4 categories that Doug, that I saw that Doug deserved to be nominated. One, his contributions through industry work in the petroleum industry, managing and mapping and conducting studies here with the Utah Geological Survey. And then his number 3, volunteer activities for the Utah Geological Association as well as other societies. And then his publications. So let me just go through some of this, because some of you may not know all of it. Doug worked in the petroleum industry for 10 years for Placid, primarily in Utah, working in Utah, generating prospects, subsurface mapping, and conducting well site work throughout Uinta Basin, Paradox Basin, and especially central Utah thrust belt. Now, Doug will tell people that when he drilled a lot of the wells in the central Utah thrust belt in western Utah, that his biggest accomplishment by doing that was telling other people where not to drill. Okay, but in reality, it did really help. His work there helped greatly increase the understanding of this very, very complex and relatively unknown geological area. So that was a huge contribution. So, and he was manager. Not only was he a geologist working in this area actively, but he was also managing the Placid office here in Salt Lake City at that time. However, when Placid closed their Salt Lake office, Doug was assigned to go to Turkey. And in the presentation here, maybe you saw some pictures of Doug when he was in Turkey. And I can't remember exactly how long you were there. There's one right there, Doug in Turkey, some of the ruins there. But he had some adventures there as well, besides doing geology. He was there during the time of the first Kurdish revolt, and apparently came and surprised a group of very heavily armed men, not in uniform, for which they had to screech their cars around, their vehicles around, and hightail it out of there to the sound of apparent gunfire. So, after that, Doug returned to Utah, surprisingly enough. And then in 1986, he joined the UGS here, where he's been ever since. And the time, so in the time here at the UGS, he has served as hazards program manager for the hazards group, deputy director. Maybe some of you now realize that he has been deputy director. And then since 1990, he's been with the mapping group here, the mapping program. But then he ventures every once in a while to the dark side and works with us in the energy minerals group as well. So some of his current and past projects, he has been, of course, geologic mapping, as many of you know who went on the field trip this year in the Uinta Basin and Uinta Mountains. He's done regional stratigraphic correlation of Middle Jurassic for many years with Helmut Doling, Bart Kowalis, and others. Throughout Utah and other states, he's been doing correlation work of the Jurassic-Triassic boundaries and so forth, looking at eolinite reservoirs such as the Navajo and Nugget sandstone. He's evaluated Mississippi and other Permian to Permian organic rich source beds, and then looked at done stratigraphic studies throughout the fold and fault belt, and then regional. He's even done some geothermal work. And so quite an accomplishment in his near 30 years here at the UGS. Next, he's been president of the Utah Geological Association in 1985. He was president, and that's where he got first started getting even with me, because in '84 I got him on a field trip, and he made me a field trip leader for the UGA. And I believe one of the books here was the guidebook from that year when Doug was president. The other activities, especially that he's done for UGA, is he's been the editor or co-editor for 5 UGA guidebooks, which is an incredible accomplishment, including the popular Park Guidebook and the Park Trails Road Law Guidebook, both in their 3rd editions. He served as a number of chairmen, publication chairs, AAPG delegates, field trip chairs, and he's led around 20 field trips, including the one that we just did. A lot of these field trips have not just been for UGA, they've been for AAPG, GSA, universities, middle and high school groups, and the Utah survey as well. I'm trying to educate the future generations of geologists and so forth. One of the other things he's done, he's helped a lot of students over the years, particularly at Utah State Utah State, University of Utah, and BYU with their master's thesis, particularly in the areas of mapping. And so you can always count on Doug. If you want to know something, you can call Doug, and he'll know it. He has tried to explain to me, I don't know how many times, his Middle Jurassic correlations and the understanding of his J1, J2 unconformity, and I'm just too dumb to understand it all. But I keep asking him, and he'll keep trying to explain it to me. Other things he's done, he's been very heavily involved in helping the Utah Fieldhouse Museum in Vernal with their natural history displays in terms of geology. He's also helped with the Ashley National Forest and their displays, and then along the roadsides that you see along the scenic byways. The byway there at Flaming Gorge had a lot of mistakes in it, and Doug is responsible for correcting all of that. Next, Doug has been, the next thing is his publications. Believe it or not, he has published over 70 technical papers and articles. Either he's been a senior author on 40 of those, which is an amazing feat for anybody. And he's published 15 geologic maps, mainly in central Utah, and then of course in the Uinta Basin and Uinta Mountains, particularly in the eastern part, and he's working on 6 more as we speak. He's been the author or co-author on 40 abstracts, which means they were presented at AAPG, GSA, and other meetings, 40 of them. So that, I think you can understand why Doug is very worthy of being awarded this. This is a huge amount of contributions he's made over the years. But I would be remiss if I didn't tell a few little anecdotes about Doug over the years. And let's start with one. We go way, way back, about 25 years ago. And Doug, at that time, was serving as deputy director of the UGS, and we were up at Research Park. And at that time, we committed a terrible atrocity as a survey. We actually torpedoed an industry event that had political friends with the governor's office. And so then Governor Bangerter sent his lieutenant governor to the survey to chat with us about cooperating. And we were kind of nervous with with the lieutenant governor come to chew us out, and so we all got gathered in the conference room. We were up at Research Park, dressed in maybe Bryce remembers this, Craig and so forth, but we all got dressed up in their nice dress pants and dress shirts, ties, sport coats, and all that. Doug walked in wearing boots, jeans, a big belt buckle, cowboy shirt, and the lieutenant governor looked around, looked at all of us, looked at Doug, pointed at Doug and said, "That guy, that's the only guy in this room who looks like a real geologist." And we all sheepishly hung our heads in shame. I mentioned that Doug and I have been friends, but have tried to kill each other a number of times. Doug and I have done a lot of field work together, and I tend to roll rocks down on him for some reason. So a number of years ago, we were working together and measuring a section of the Twin Creek limestone at the Devil's Slide cement quarry where we got permission to go in there. And Doug said, go over that way and start measuring how thick it was. And it wasn't too long that I realized there was all these little things sticking up all over the place. Well, they were blasting caps, and Doug had sent me into a mining field. So, finally, one other little story, because I know you want to hear Doug's presentation, get his award. But a few years ago, I'm on a committee with BYU in terms of their College of Physical and Mathematical Science. And every year BYU has a spring student research conference where they have hundreds of student presentations, and I go down there to help chair geology sessions where students present their work. And so a number of years ago, I was chairing this session. One of Bart Kowalis' students was making her presentation on her mapping project in the eastern Uinta Basin, kind of near Sheep Creek geologic site where we went on the field trip. And while she was making her presentation, in shuffled Dr. Lehigh Hinsey. You could just see fear on all the students, especially this young lady that was up in front of everybody as here the master. They'd never had him before. Of course, he was about 88 or so at that time. And so they knew he was going to be firing questions at them. And I, as the chair of the session, wasn't about to tell him, Dr. Hinsey, it's time for you, we need to move on, So I couldn't do that. So he started in on this poor lady and said, now some of you have heard this story, I apologize, but she started saying, now if you'd read my book, you'd know that isn't the Amsden Formation, that's the Morgan Formation. And then he said, why did you put that contact there? If you'd seen my map, you'd know that it was this way and that way. And she was starting to get a little frustrated and beads of sweat coming down her forehead and all that. And finally said, why did you put a fault in there? How come you think there's a fault there? And finally, out of frustration, she said, well, Doug Sprinkel said it was there. So Doug gets blamed even when he's not even there. So anyway, just in conclusion, I wanted to mention that in 2003, when Lehigh Hinsey accepted the very first award that bears his name, he got up in the same room and gave his presentation, his acceptance on the speech. And in the course of his speech, he said this, and quote, there are two people that he says, I have the highest respect for their contributions to geology. I kind of thought, well, he's going to talk about me, but actually, one of his students. But no. He said he had two people that he had the highest respect for. First was Helmut Doling, which, of course, Helmut was the second award winner of the Lehigh Hinsey Award. And, of course, the second person that Lehigh Hinsey said he had the highest respect for was, of course, Doug Sprinkel. And now most of you know that Helmut, they're all still alive, sorry. Dr. Hinsey passed away a year and a half ago at the age of 93. And I can assure you that if he were still with us, he would be enthusiastically endorsing this year's award winner and thrilled that Doug received the award. Doug Sprinkel. Thank you.
You do. Where's that? Before you start your talk, on behalf of the Utah Geological Association, I'm extremely honored to award you this plaque for with a Lehigh Lindsay Award.
Thank you very much,
Congratulations.
Jason. Thank you. Thank you.
I was remiss, I didn't mention that there's a cake over here also. I don't even know what it says on there. I didn't order it, so I'm not responsible for that.
Okay.
We do have cake, so everybody should get a piece before it disappears.
Okay. Now, that kind of reminds me of a story, and it has to do with Tom Chitsey. Is that he was given a talk at a Rocky Mountain Section AAPG. So the announcement of this cake is kind of in line with this. But he was given a talk. It was toward the end of the day, of the last day, and there was only a few people in the audience anyway, listening. But what was there, was listening eagerly to Tom talk, and the doors burst open, and a guy yells, "Free beer in the reception area." Everybody got up and left, except for one person, and he stayed there, and Tom finished his talk, and after it was done, he asked if there's any questions, and the one person that was there stood up, and he says, I think your interpretation of these rocks are, and he said a nasty word, but I won't say it, he says, are full of crap. So anyway, so I was worried that everybody was going to hustle over to the cake. So, okay, if I'm going to talk from this side over here, and let's see what does what. That's the point. Okay. And if you can't hear me, let me know. Just wave your hand and all that, and I'll try to speak up a little bit. First of all, I am extraordinarily honored to accept this award and receive this award. I had known Lehigh back in my placid days, and he was one of the kindest gentlemen and teacher that I had ever known. And I'm really grateful for receiving this award. But as you all know, nobody does this stuff alone. We've had help throughout our careers with a variety of folks. And before I get started, I'd like just to mention a few. One, of course, is Tom Chitsey. I really do value his friendship and be able to work with him. He's a real treat to be in the field with and to discuss geology. But I also am really grateful to Helmut Doling, Bart Koalas, Jerry Wanders, and Paul Keeney, who all have helped and worked with me on this Middle Jurassic stuff. I kind of fell in love in the Middle Jurassic back when I was with Placid. Helmut was doing the same thing in a different part of the state. In 1999, we sort of joined forces to try to get at the Middle Jurassic on a region-wide sense. And you're going to see a little bit of just a taste of it today. And Jerry Wanders, I've worked with Jerry Wanders. He's a palynologist. I've worked with him since 1979. And he's still working, and we still collaborate on stuff. So, and I also appreciate Carol Daler and Paul Link. Carol Daler is at Utah State. Paul Link is at Idaho State. And them and their students have greatly helped in the mapping of the Uinta Mountains, particularly the Uinta Mountain group, in helping break down the eastern Uintas into just a Utah, or the Uinta Mountain group into several formations. And we have now mapped those formations, and that's coming out in the Dutch John, latest version of the Dutch John map in a couple of years. And because of that mapping and recognizing the formations within the Uinta Mountain group, we've been able to recognize these structures that we previously haven't really been able to get a handle on. And what kind of led to kind of my thinking of basin inversion and the uplift of the Uinta Mountains and the structure, the internal structure of the range. And so we're going to talk about that a little bit and show you a little bit of the reason why I've been kind of thinking about this. I think maybe folks have been thinking about this for a while. I'm just a little slow. It's taken me 30 years to kind of get at this. But we're going to look at that, and I'm going to show you kind of an example of how the reactivation of this late Neoproterozoic structure has affected sedimentation through time, but particularly in early Middle Jurassic time. And this is kind of new. Some of this stuff is kind of new. Okay, let's get started. Basically, I'm going to just do a brief overview. We're going to talk about this late Neoproterozoic deformation and the reasons why I think we have that deformation. And then, of course, we'll talk about how it's affected sedimentation, particularly in Cambrian through Silurian. And then again, we'll finish up with Middle Jurassic stuff. Now, the Uinta Mountains, of course, are in the northeast part of the state. Salt Lake City is right in here. Utah Valley right here. The Uinta Mountains, of course, is an east-west range, which is a little unusual for Utah. And it joins the Uinta Basin to the south and the Green River Basin to the north. We know that this is a laramide structure, and that most people just think of it as a laramide structure. But what I think I will show you here is that there's more to the range than just a laramide structure. John Wesley Powell first described the Uinta Mountain uplift as this big arch that ran east-west, and he published it in his 1876 report in Atlas, and he noted that the axis was not a straight line, but it was curved. And so even back in Powell's day, the unusual shape, the east-west shape of the range, but then the very eastern part has kind of a southeast turn onto it, and he had noted that early on. Wally Hansen, who did a lot of the fundamental mapping and a lot of the fundamental work in the eastern Uintas in prepping and understanding for what would become the Flaming Gorge Dam and Flaming Gorge Reservoir, he noted that the Uinta Mountains too had this east-west direction with a little funny southeast turn on it at the end. But he had actually mapped out that the Uinta Mountain anticline is actually two separate domes, a west dome and an east dome, with a swell in between. And if you note this fault right here, this is a fault that actually cuts Pleistocene age deposits on the Diamond Mountain Plateau. But it's kind of instrumental where it is and its trend. If you look, it's sort of on line with this swell that Wally Hansen had defined. And so basically the Uinta Mountains, was uplifted in laramide time along a series of high angle thrust faults on the north flank that are segmented. This is the north flank fault, the Uinta fault, there's the Henry's Fork fault, and then the Sparks fault over here. But there's also a fault on the south side, which is the Uinta Basin Mountain Boundary Fault, which is mostly a blind fault, meaning it doesn't get to the surface. However, the mapping that I've been doing in the Uinta Basin, I've found segments of it now where I actually see rocks of Eocene age being cut by the fault. And it's pretty much on line with where it is. And my guess is this is also a segmented fault, and I'm still trying to work out some of the structure there. Laramide orogeny, of course, is 75 to 34 million year range of deformation. Again, it's these high angle to moderate angle reverse faults. On the south side, we can see this is essentially along a seismic line that Don Stone had published in 1993 through the Utah Geological Survey, and essentially we can see the faults that control Asphalt Ridge, Raven Ridge are all, for the most part, in a blind system. Although there are places, like I said, that we can see the uplift or see deformation of Eocene age rocks. Now the rocks of the Uinta Mountains and Uinta Basin area, there's quite a variety of rocks represented by Precambrian, Paleozoic, Mesozoic, and Cenozoic. What we're going to do is we're going to focus in first on the Neoproterozoic down here, the Uinta Mountain group, And we're going to take not really a look at the rocks of this area, but more look at what is missing. Because here you have late Neoproterozoic, and sitting on top of it throughout much of the range is the Cambrian Lador sandstone on the east and the Cambrian Tinic on the west. And in a lot of parts in the central part of the range, these rocks are not present, and the Madison limestone sits right on the Uinta Mountain Group. And again, I think that I'll hopefully kind of explain why I think that is. And then we're going to look at the Middle Jurassic. We're going to look at this section right here where we have the Carmel Formation, Twin Creek, European formations. Before we get too much started, too much further along, I just want to mention the feature called the Cheyenne Suture Zone, which has been known for quite a while. Its exact position is in debate as to whether it's here or a little bit further to the north. But essentially, this suture zone separated the Archean Wyoming craton from the accreted Paleoproterozoic rocks. And that is what it basically set the foundation for the east-west trend of the Uinta Mountains, and it's the thing that has been reactivated through time. At this time, it was a transfer, well, like just a boundary fault where these rocks here were being accreted up on the Wyoming plateau, or the Wyoming craton. Again, from Condi, you can see with his view of where the Cheyenne Suture Zone is in relation to what would become this basin that deposited up to 16,000 feet of Uinta Mountain Group. So again, the north flank of the Uinta Mountain Group is very, very close to where this fundamental crustal weakness is located. Now, in the eastern Uintas, when I first started mapping the Dutch John 30 by 60, we had, of course, the Red Creek Quartzite, which is a Paleoproterozoic unit. And then we had this great pile of sedimentary rock. They're not meta-sedimentary, they're just plain sedimentary. There's no meta about it. These are not metamorphosed in any way. A lot of the shale units and some of the fine-grained silty units have a lot of mica in it, but all the mica is detrital coming off of the Wyoming craton. And this big pile of rock was deposited in a faulted basin, and the big fault was on the north side up against the Wyoming craton. And at that time, the Jesse Ewing Canyon was a defined unit, and it served as the base of the Uinta Mountain Group as it sat right on the Red Creek Quartzite. And it's mostly a conglomerate that grades up into a mudstone. And it was in these mudstones that I collected some samples, sent them off to Jerry Wanders, and found that they were loaded with organic matter. Mostly it was all cyanobacteria and organic fragments. But the amazing thing is that none of the organics were cooked. They were all kind of in the oil window, so they weren't overly cooked. The other unit was the Red Pine Shale, which is the top of the Uinta Mountain Group, and it's mostly an organic-rich shale. It's equivalent to the Chuar in the Grand Canyon area, and it is organic-rich, and so much so that it is considered a potential source rock in this region. Everything in between was this great big pile of quartz aeronites and arcosic sandstones and conglomerates and micaceous shales that was just called the Uinta Mountain Group, and that's how I mapped it in the first version of the Dutch John 30 by 60. Since then, with the help of Carol Daler and their students and Paul Link, and specifically Dan Rybczynski, who actually helped me with the mapping in 2008 to break these things down, is that we have these now divided into a series of informal names. Above the Jesse Ewing Canyon is the formation of Diamond Breaks, Outlaw Trail, Krause Canyon, Hades Pass. And Hades Pass is a unit that's a already named but informal unit in the western Uintas. All these others are just in the eastern Uintas so far. The western Uintas have their own set of names. But all these organic-rich mudstones throughout this section has these polynomorphs, these fossil cyanobacteria. And what was really interesting to Jerry, anyway, Wanders, is that the stuff that we got out of the Jesse Ewing Canyon tended to be these just carbonaceous filaments and these big Liazospheras, very simple-celled organisms. They're single-celled and simple-celled wall-type organisms. By the time we got up to the Red Pine Shale, we started seeing things that were a bit more complex, with more complex cell walls, and they were colonial. So we were seeing things going, the organic matter, the cyanobacteria, going from simple-celled single organisms up to more colonial organisms that were a little more complex. The age of the Jesse Ewing Canyon has been dated from detrital zircons out of the Outlaw Trail, the Jesse Ewing Canyon, and out of the Red Pine Shale of about 770 million years at the base, and that we think it is as young as 642 million based on its correlation with the Chuar, which has been dated radiometrically. So it's a kind of middle Neoproterozoic unit. And you can see the ranges of polynomorphs and the different kinds of polynomorphs we have. Again, these are all up in this upper part. That's all these really complex things. So this was instrumental into being able to recognize these formations and map them, and then starting to see the structural discontinuities as a result of it. Now this is a very preliminary stratigraphic chart I put together showing the informal formations of the Uinta Mountain group in the eastern Uintas, and the informal and formal members or formations in the western Uintas. Again, the two things that kind of go across is the Red Pine and Hades Pass. But we do see that some of these formations are equivalent to this Krause Canyon, the Moosehorn Lake, formation of Moosehorn Lake, which is the oldest exposed unit in the western Uintas, I believe is equivalent to the formation of Outlaw Trail, which means there's still more section below the Moosehorn Lake. But again, I can't stress enough how important this work by Carol Daler and Paul Link and their students is for understanding this. So what's the evidence for a late Neoproterozoic deformation? Well, the Uinta Mountain group was, again, deposited in a basin. Up to 16,000 feet of rock was deposited. That was both fluvial and marine. So it's a fluvial and marine sort of interbedded unit. And a lot of the sediment source came out of the east, northeast. Some came directly off the Wyoming Craton, and the sea kind of came in from this direction and transgressed and regressed. And so this was a basin that in late Neoproterozoic time was uplifted. And it was uplifted as a result of mapping these units, or recognizing the uplift as the result of mapping these units out and realizing that the older part of the Uinta Mountain group, this Krause Canyon stuff down here, was actually right next to Red Pine Shale. So we had quite a section that had been reduced because we had placed something much lower down section up against or near something that's very near the top or at the top of the Uinta Mountain group. Also, we noticed that the formation of Hades Pass, which is this big red unit all the way through here, again, it had a variable thickness along this projection of this fault. Again, we all knew about the fault that runs along the north flank of the Uintas and along the south flank of the Uintas, particularly the south flank fault. But this fault is a new feature. This is something that I am proposing as a result of the discontinuity in the stratigraphic, the stratigraphy of the Uinta Mountain group. Plus, it aligns along this fault. This is that fault that cuts Pleistocene age deposits. Also along this fault, right about in here, is the Dyer Mountain Mine. So it's an alignment of the mineralization right into this area. And also, as we get up into this area, we can see evidence where the Gilbert Peak erosion surface, which is a 34 million year old surface, or formed 34 million years ago, is offset by this. And Wally Hansen first noticed that the eastern Uintas has been lowered down relative to the western Uintas. And this, I believe, is the culprit for that. When we look at where all the high peaks are, the Uintas, they're all here in the west. All the 12,000 plus foot peaks over here in the west. There's no peak over here in the east that's over 9,500 or about 10,000 feet. So there's a difference in the elevation, in the topography. Also, the South Flank Fault seems to terminate very close to this thing here. So something as big a deal as this, how come we haven't seen it before? How did I miss it the first time around? Well, a lot of it was that you look at the Paleozoic and Mesozoic rocks and you really don't see any major offset along this thing. What you do see is oblique folding and some minor fault segments, but nothing major. What we do see is in Neoproterozoic rocks, there is significant offset. So again, this, I believe, is responsible of, that in part the basin itself became inverted. The eastern Uintas was thrust up over the western Uintas and basically formed an arch which becomes the Uinta-Cortez arch, or sometimes also known as the Tooele arch. And that is probably what is responsible for part of this offset and sort of turn of the range, is that it formed in late Neoproterozoic time. So now we've got, in late Neoproterozoic time, we've got this arch, or this anticline, which would likely represent a highland. The sea is now, the late Precambrian sea is now gone. And this stuff, the Uinta Mountain group was exposed at the surface. Oh, the other thing that's really interesting is if you look at the structure along here, there is a tilt to the west of the Uinta Mountain group. It's not only got a little bit of a fold, which is then accentuated in Laterite time, but it's also plunging to the west. And up on Ice Cave Peak, you can look into White Rocks Canyon. This is the Red Pine Shale. And you can see that the contact with the overlying Madison limestone is unconformable. And also there's no lador or tinic here. So this was a paleo high at that time. And after the basin was inverted, there was a period of erosion which formed a paleotopography, and that because the range was tilted, as you go to the east, it started planing off, plus you still had those older part, the thrusted older part of the rock exposed on the east, in the east part of the range. But as the middle to late Cambrian seas kind of flooded into this region, they filled in the paleo lows, and they didn't get across the paleo highs. If you ever go up the Duchesne River drainage out of Hanna, you'll go through Mississippi, well, the middle Paleozoic rocks, and you'll get down to the tinic, and you'll go through about 200 and 250 feet of tinic, and you continue, and then you drop into the Red Pine Shale. But if you turn around and look, you can see the tinic going from 200 feet and pinches out against the Red Pine Shale, and you have Madison sitting right on Red Pine Shale, and it's just absolutely dramatic. It's just unbelievably cool. So again, I think that, looking at the relationships that we see above and below this unconformity, the fact that we have the older part of the range being uplifted and faulted up, and again, this I believe is the start of what is the Uinta-Cortez-Tooele Arch. And if you look at some of the paleogeographic maps that have been published, again, in Middle Cambrian time, you see this. You always see these little fingers sticking out in an east-west sense, which again was part of, I think, this Uinta-Cortez high. Even in Ordovician, it's even more pronounced. And this is from Lehi Hensey and Bart Quallis's Geologic History of Utah. And so we see this pattern repeated. Silurian, same kind of thing. Mississippian, the seas got high enough that that basically you don't see much in the way of this east-west structure. but in early Paleozoic time, we do see it. So let's take a look at the Middle Jurassic for a moment, or at least the lower part of the Middle Jurassic. And this is part, whoops, back up just a minute. Press the wrong button. Okay. This is a part of this study that Helmut and I and Bart Koalas, Jerry Wanders, and Paul Keeney have been working on for a long time. And we've actually had, Helmut and I and Paul have measured close to about 170, almost 200 measured sections throughout the state. Plus, we use some existing published sections. Well, we measured 120 sections, and we used an additional 70. And then I've examined close to about 230 wells in this region, basically identifying the various members of the Twin Creek, Arapian, and Carmel formations, and correlated that. Part of our measured sections work. We collected samples for palynology, and we've got a really strong suite of palynomorphs from some of the members that helped us with the correlation. In fact, it was Jerry's palynology that when I was with Placid, we were drilling wells down here in central Utah, and of course we had this Arapian stuff. And everybody, including all of our drilling personnel, say, okay, we're in this Arapian stuff. When we're going to get down to the Navajo sandstone, which was our target. And the Arapian, if you look at the surface, is this wildly deformed unit that has got variable thickness, and predicting when you would get through this was extraordinarily difficult. But what we noticed is that just above the nugget sandstone was a carbonate section of rock, and the carbonate section rock was better behaved. I mean, you could count on its thickness, you could count on what it looked like, and so when we hit that carbonate, we knew that we would be only within so many feet or hundreds of feet till we got to the Navajo sandstone. Well, as I continued to look at the well logs, I was trying to find anything that I can correlate with, like the Carmel and that area there, and yeah, there sure was some resemblance to it. But what I did is I actually looked up in the Wyoming thrust belt, the northern Utah-Wyoming thrust belt, and lo and behold, I found exact matches to the members of the Watton Canyon, Boundary Ridge, Rich, Slide Rock, Gypsum Springs. And I said, well, by gosh, you know, we're kind of on depositional trend of that stuff, and as you go to the east, things are changing and thinning, even though the log characters are somewhat similar, but the lithologies are different. And that was kind of an eye-opener. And that was like 1981 that I kind of hit on this thing. And we started to design our casing program around that idea. And based on just that one observation, we were able to reduce our drilling cost. At the time, our drilling cost for a well was down to 15,000 feet, was about $10 million. And we were able to get it down to about $2.5 to $3 million, just based on that. Mainly because we could design a casing program to better maintain hole integrity and be able to evaluate these underpressured reservoirs in the Twin Creek and in the Navajo sandstone. So Placid was tickled pink, and so they kind of let me do whatever I wanted to do, and so I was busy out there measuring sections and doing stuff, and sort of set me off on this path of this Middle Jurassic chase. So what these dots here recognize, or what these various color dots mean, because we're looking at right now just Gypsum Springs and Temple Cap Formation, which occupy the same stratigraphic position. They're above the J1 and below the carbonate stuff of the Twin Creek and below the carbonate stuff of the Carmel. And the green dots represent the Temple Cap rocks. And we're going to go through why I believe Temple Cap is all the way up here. The orange dots represent where I can identify gypsum spring in the wells as well as what we measured. And then we'll talk about this stuff down here in southern Idaho and southern California, which is the Aztec sandstone. So the temple cap, again, was once thought to be restricted to southern, just this part of Utah, this southern Utah. But as a result of palynology and radiometric age dating, we were able to, and just recognizing lithologies from our measured sections and from the well work, we were able to recognize that the rocks up here in the thrust belt were actually temple cap rocks and not gypsum spring. The temple cap actually has three lithofacies. It has kind of a western lithofacies, it has a central and an eastern. This is all kind of a marine to marginal marine and interbedded coastal dune package of rocks. And the further west you go, the more marine it is, and the further east you go, it becomes pretty much exclusively aeolian. So in the western part of the range, over here by Gunlock and north of St. George, we have the Temple Cap Formation, which we call the manganese wash member. And it's all this red, kind of red, planar bedded sandstone. It does have some small scale low angle cross beds. The sandstones are rippled. No significant aeolian beds in it at all. We do have the same thing with siltstone, but we do have gypsum and limestone, which is very silty to bioclastic. And so this is typical of a good marine to marginal marine interval. This unit also has ash beds in it, and we've dated those ash beds at 173 to as young as about 171. So that sort of started getting us an idea that, my gosh, you know, this is not Bajocian, this is actually a little bit older. It's Alanian, which is the lowest part of the Middle Jurassic. Now, if you go just to the east, not too far, at Zion National Park, you actually you see that the temple cap takes on, the temple cap takes on a different character. We have this basal Sinawava member, which is a marine kind of a red unit. Again, it has all the indications of a marine unit. Then we have the white throne member, which is an aeolian unit, which represents these coastal dunes. And then it's capped with the Esplin Point member, which is a new member that, again, is marine. And then on top of that is the Carmel Formation. It's the Co-op Creek member of the Carmel. So we have a little bit different look. We have an area now where we have the marine inner tongues with this big aeolian unit that protruded out into the marginal marine basin as a result of transgressions and regressions. Now, looking at the Wolverine well, which made a discovery at Covenant in central Utah, which is a significant discovery, and above the Navajo and below the Slide Rock member, they had this interval that they called the upper Navajo, because it had this big aeolian unit in it with red units in between that they felt was just intertidal or interdunal wadis. But what they had discovered is that there was marine Middle Jurassic polynomorphs in the thing. So it couldn't be Navajo. It had to be Temple Cap or Gypsum Spring. But because of this red unit, which also had glauconite in it, and we had this big aeolian unit with these little marine inner tongues that have marine polynomorphs capped by another marine unit, then it just goes right up into the slide rock. So we had a marine tongue, aeolian, aeolian tongue that is part of the regression, and then another transgression that basically just kept transgressing up into more shallow marine carbonates. Now on the east, we had the Navajo sandstone, and this unit that we call Temple Cap is formerly the Page sandstone, and above that is the Carmel. And the reason why we now call that the Page is because Bill Dickinson and Bart Kowalas and a student at BYU basically found some ash beds that are in the swells of these aeolian units. And the dates that they got were both argon-argon on sanidine and uranium-lead on zircon. And gosh, you know, it's 171, 172, 169. That's temple cap age. And that created a problem because the page was supposed to sit on the J2 unconformity, and the temple cap is sandwiched between the J1 and the J2. And so now we've got this interval that was supposed to sit on the J1 that, or sit on the J2, that it couldn't be the page if by definition it's supposed to sit on the J2. So we proceeded to look at other places like at Angel Point and at Judd Hollow, and we got detrital zircons there, and again they showed up at 169, 170. So this was a more widespread unit than we thought. So here we got this problem of the J2 and J1. The J1 sits on the Navajo sandstone, and that this unit called the temple cap, which is equivalent to this, has got to be sitting on the J1 and not on top of the J2. The J2 would be this thing right here. But because of the deposition that we see in the manganese wash member and in Esplin Point member, is that this is just a sedimentologic depositional increase in sea level, and we don't see a real break in lithology at all. And Bart Kowalis, who had dated all the way from the manganese wash all the way up through the Carmel, he found that there was no significant break in time, and we could not ever find anything that looked like an unconformity. So we've sort of abandoned the whole idea of the J2 unconformity down in southern Utah. In fact, we abandoned it south of the Uinta Mountains. And that what we see is the J1 unconformity, and in this area here we actually have a little bit of a paleo high that separates out this part of the section from this part of the section. But essentially we do have the temple cap preserved in eastern Utah, or east central Utah. And if we look at, you know, just the correlation, we can see how here's the mostly all, well, it's the marine part of the temple cap, and you can see where we start intertonguing with the Aeolian units, and as we go in this direction it becomes mostly Aeolian, but in many places we'll see a little bit of the Sinawava, that little bit of the marine stuff. Okay, the gypsum springs. Now that's denoted by these yellow, orange colored things here. And again, it's a siltstone, mudstone, sandstone unit. It's marine, it's got gypsum, it's got limestone, solution breccias, and bioclastic limestones as well. And Bart and I have dated that now at 185. This is based on argon-argon on sanidine and uranium lead on zircon, and both agree that it's 185. This is 12 million years older than the temple cap. So even though the temple cap and gypsum springs occupy the same stratigraphic position, it's very clear that the gypsum springs is a much older unit than the temple cap right here. And we're going to talk a little bit about, in a couple of slides, about the significance of that. But think about it. I mean, think about the Sundance Sea, which is thought to be providing the marine waters for these rocks. And finally, down here in southern Nevada and southeast California, the Aztec sandstone is preserved and exposed, and it was thought to be correlative to the Navajo sandstone. But Kathy Busby and her co-workers dated this dacite lava flow, and lo and behold, using uranium lead zircon, and lo and behold, it's 172 million. So it's likely not Navajo. It's more than likely temple cap equivalent. And that in this area, well, in all these areas, this is not the full section. This is just the upper part. But in other areas, there are where the section has been measured, like in the Cowhole Mountains and Old Dad Mountains, at the Valley of Fire, the Spring Mountains, interbedded with the Aeolian sandstone is red rippled siltstones and sandstones. And in Southern California, we actually get some limestones, little thin limestones, and most of them have been cooked to marble because of the igneous activity that's going on. And so here we have what I think are rocks that are very, very similar in age and of course similar in depositional style to the Temple Cap. So we got to resolve the age difference. If all of these rocks that we looked at, the Gypsum Springs, Temple Cap, Aztec, are all supposed to be time equivalent and part of the Sundance Sea, that here we've got something that's 185 million years old. That's on top of it is the slide rock member of the Twin Creek, which is 168 million years old. Down in this part of Utah, we've got the Temple Cap that's 170 to 173, and it is overlain by the by rocks of 169 of the Carmel, Co-op Creek limestone member. So and then down here we've got 172 overlain by a bunch of volcanic rocks that have been dated at 167, which are equivalent to the middle part of the Carmel. So how do we get a sea connected this way with 185 up here with no 173, and down here no 173 or no 185, but a bunch of 173s and 170s? So I question whether or not the sea actually came in from the north for the Temple Cap. And I think this is where the late Neoproterozoic high comes in, is that feature is setting right along here. And if you notice that in this area and in some of the other slides, in this area, there's no Temple Cap or Gypsum Spring in this area. It's gone, or it was never deposited. So looking at our stratigraphic correlation chart, we can see the Gypsum Spring is down here at 185. Essentially, it's correlative to at least part of, or maybe part of the Glen Canyon group or Navajo. We have Temple Cap up here that we've correlated in the central part of the state as well as in the southern part of the state. So looking at, sort of the traditional idea of the Sundance Sea coming down into southern Utah at 170, and looking at the green dots, which are the Temple Cap rocks, and the purple triangles are the radiometric ages, looking at where the Gypsum Spring is with the orange dot, and this red thing is the 185 date, and then you look at over here the black dots and well symbols, that's where the Temple Cap is not present. So clearly there's, to me, something quite not right. How do you get something to come down here and not be present here unless, again, you have it come down here and then you regress it back, which is okay, and then you start eroding things up here. But then to get marine deposition down here, then you'd have to sneak the sea around the edges, which is a possibility, and it's one of the possibilities that we're looking at. So instead of having this Sundance Sea coming in from the north that basically deposited the Gypsum Springs and Temple Cap, I'm going to propose that what we had is the sea coming down at 185 and basically ponding up against the Uinta Cortez high, and that we had no deposition. This was all just Navajo surface, basically the J1 surface exposed at 185. Then at 173, we had a regression. This area here began to erode, forming the J2 unconformity that separated the Temple or the Gypsum Springs from the slide rock member of the Twin Creek. But we have marine stuff here with aeolianites interbedded, and gosh, right here, that's just not that far from southern Utah. And again, if you take out the extension, it's even closer than that. And so I believe that the source of the Temple Cap Sea came from California, came from the south instead of from the north. Now that was short-lived because we did have a flood of the Sundance Sea coming down for deposition of the rest of Twin Creek and Carmel. And if you look at, this is stuff that Jerry and I did in 1984. And if you look at this, we have, the thickness of the rich member, which is Upper Co-op Creek and Carmel land. is that we have a little bit of a thinning and positive, right? Well, not a positive, but a thinning of the rocks right in this area where the Uinta-Cortez High is. Looking at the paleogeographic setting, this is all open marine at this time, at 168. Then about 164, which is where we go from open marine to restricted marine. This is essentially the lower carbonates of the European Formation going to the 12-mile canyon member of the European, which is the unit that you go down there and see that it's all twisted and deformed and it's got the salt and just is just tough to work with. But you can see that this thing formed this nice little embayment or little basin because the seas began to regress back in this direction. And again, I think that this Uinta-Cortez High actually served as a buttress, a little bit of a subsea rise that as sea level fluctuated, at times this became really restricted, hypersaline, which allowed for the deposition of salt, but then it floods in from time to time, which then you can get sort of hypersaline marine conditions, but you get carbonates and calcarenites being deposited. And this is kind of the cartoon that we envisioned, is that we had we called this the severe highlands at that time, but I think now this is what Chuck Thorman calls the Elko orogeny, and that basically formed the boundary on the west. Of course, we had land masses now on the east. This connection with the California area has been cut off, and we got this hypersaline body of water sort of ponding up against this, whereas the Leeds Creek member, which is the equivalent to the 12-mile canyon, Leeds Creek member of the Twin Creek, is up here to the north as open marine waters. And so I think that what we're really seeing is that this paleo topographic high, which you know was formed in late Neoproterozoic time, or probably even earlier than that, basically is responsible for sedimentation and control of sediments through time. And you know, and part of this is that we are also looking at a deformational event that we really didn't talk about, that I'm working on right now, that is sort of you know, kind of a Jurassic, late Navajo, late early Jurassic to early middle Jurassic deformational event, which again may have created these paleo highs and reactivated some of these highs like the Enthympadre, this ancestral Uinta mountain group thing. So those are things that are coming and I'm still working on. Thank you very much. Any questions? The Perry Canyon Formation is jungle, so it was being deposited when that basin inversion was going on. It's a little bit jungle. Yes. I was never good at the end of it. Washington built on it depends on your definition. I call it a faulted basin, but yeah, I mean, if you look at the original definition of a locogen, yeah, you call it a locogen. I don't think it's a rift valley in the true sense of a rift, because there are no volcanic rocks involved at all. But you know, a faulted basin is kind of the safe, squishy way for me to talk about. And we don't know if there's a southern part of it. You know, that we know that we have the major fault on the north side. The south side is in question as to whether that Uinta Basin mountain boundary fault is the south side of the basin. Don't know. We don't have any well control out south of that to be able to tell us one way or the other. Sorry about that. I lost you guys online. Any other questions? Yes. Yes. Well, Carol Daler and others, yeah, they seem to be or at least that's the conventional thinking, is that they are isolated basins in two separate faulted basins, essentially. But Carol Daler and her workers have proposed that there was actually a connection, a seaway, and that these were part of that main big seaway just to the west. The Pahrump group in southern Nevada and southeast California, again, is another unit that, again, appears to be about the same age as the Chuar and the Uinta Mountain group. So they put that as part of the Chuar Pahrump. Let's see how they do it. Chuar Uinta Pahrump connection. They call it the chump. So if you see chump, that's what they call it. Okay. Thank you very much again, guys.
What do you think of turkey now?
What's that?
What do you think of turkey now?
Glad I'm not there. Yes, it is. And where I was working is where a lot of the refugees are now, and a lot of the military